This is the review of Exam 3, and the first problem was a problem very similar to the one I handed out in class as a class activity. And what we're doing is just trying to find the tension in the string before it's cut, and then the angular acceleration after the string is cut. So the first part starts out as a straight statics problem, no dynamics at all. I ask you to draw a free body diagram, and the free body diagram in statics or in dynamics also always includes those reaction forces. I wanted to make sure that you drew those in there. You got a center of gravity here, and so then mg is acting down through there. We had to find the distance between the point of rotation and the center of gravity, and so I found that distance as 0.75. And then to do the statics part of the problem, or to do find that tension, it's a straight statics problem, like I said, and the easiest way to do it is to do a sum of the moments about O is equal to 0. And so I have a cosine component here times this lever arm, and mg times this lever arm. The sum of those have to be equal to 0, and I get tension is equal to 449. Several people left off the lever arms, either this one or both, and clearly that's not a complete equation. You have to have lever arms if it's moments. All right, and then the dynamics part is finding the angular acceleration. We'll use some of the moments about O as IO alpha. We'll find IO using the parallel axis theorem, and so it's modeled as a thin rod of 1/12 ml squared. We're going to move it using the parallel axis theorem the distance d. The distance d was that distance up there of 0.75. And we find IO as that, and then we'll plug that into our moment equation, find out alpha is equal to 6.79. If you had the version of the problem where b is equal to 3, then you get slightly different answers for all of those pieces, and that's what they've got. Okay, the next problem is this car. We had two versions of the car, one with front brakes and one with rear brakes. Let's do the front brakes one first. It's important to draw a proper free body diagram, so I'm just draw it as a box here, and I always draw the forces at the point at which they are applied. So he's going in this direction, he's traveling to the left, but since he's braking, he's actually accelerating to the right. And so I'm going to call x positive going in that direction, a force of friction applied at the front, mass times acceleration, got an mg coming straight down, I've got a couple of normal forces here. Now in this case we're going to have normal forces continuing to exist at both A and B. We're not going to have one of those go to 0 because it doesn't have the tendency to tip over the front. That just doesn't make sense in this kind of a problem. So we're going to use a force equation. Some of the forces in the x is mass times acceleration in the x, and the only force I have in the x direction is that slipping mu times that normal force. And that's going to be equal to mass times acceleration, and I get A is equal to 2142 in the times AX. And I'm going to use that in the next equation, my moment equation. So the moment equation says that sum of the moments about B is equal to the mass times acceleration of g in the x direction times y bar. So this is where we're going to use that mass times acceleration vector, and it's going to have some rotation, or it's going to cause some rotation about our point of rotation. So if I call this my positive direction, I'm going to say A. I'm going to some moments about B over here. So I'm going to have A is going in a positive rotation times its lever arm. mg is going to have negative rotation times its lever arm. That's going to be equal to ma times its lever arm. And this is also going in the positive direction as you go this way, so that ma times the lever arm is going to be a positive value. You can find out a by substituting that into there. Once I know the acceleration, I can solve for the distance that we're looking for using a constant acceleration equation. All right. And the next piece of the problem was what happens if I compare two different types of vehicles? Which one, if they have front brakes, which is going to brake faster? Well, what happens when you brake? We did this demo more than once, but what happens when you brake is you tend to pitch over the front tires. In other words, the weight kind of shifts. So the farther forward the weight is, the easier it's going to brake, because it'll have more weight on those tires, whereas opposed to here the weight is shifted in the back, and so the weight is more on the rear tire. So the one that will stop the easiest will be the one that has the weight farther forward and the weight that is higher. If it's higher, then it's going to more easily pitch over the front. So we have two reasons why this one will actually brake better with front wheel brakes, is because the CG is higher and it's also closer to the front. If you had the other problem of with rear brakes only, drawn exactly similar but slightly different free body diagram, is that it's similar in that it has all these elements, except that here we're going to apply the force of friction at the rear tires, and we're going to do the same kind of analysis. Sum of the forces in the x is mass times acceleration in the x. We're going to get something about b here is 2143 times ax. Doing our moment equation, and we're going to do a similar thing. I'm going to sum the moments about a this time. I'm going to go positive in this direction. And so I'm going to say I have b times this lever arm minus mg times this lever arm is equal to negative. In this case, the ma vector is actually going in the negative direction around point A. And then I put that and make sure you include that lever arm for the mass times acceleration vector. And you can find that ax is equal to that. All right. And then we'll use the constant acceleration equation here to find out how much time it takes to come to a stop. All right, and then again the same basic question at the bottom is if these two cars had rear brakes, and by the same kind of analysis that we did in the previous question about front brakes, the farther back the CG is from the front and the lower the CG is, the better back brakes will work. So two scenarios again. If it's lower and farther back, it will tend to make it work better with rear brakes. All right, this next problem is best. This is a cam. We did several of these. We did one of these in class. We did several in homework. This picture is maybe a little different than you've seen before, but they all work the same way. And these are best solved using the absolute approach. And what we're doing here is we want to find a relationship between a distance and an angle. So I'll just find that distance x here is equal to 0.15, which is that part, plus 0.12 sine theta, which is that part. We take the derivative twice, and I can get those fairly easily, and then I just recognize that x dot, the change in x, is actually the velocity of c as it pulls back there. So x dot is equal to velocity of c. Plug in the numbers in here, and I can get that at 0.45 or 415. And the acceleration of c is x double dot, which is right there, and I can plug those numbers in and I get that. That's really the best way to solve this. There are some other methods that you might try that can work, that will work, and you can set up a relative acceleration equation so that basically there's this distance here, and this point here would be rotating about that point. It would have an r alpha in that direction and an r omega squared in that direction. You would take the x components of each of those things, and then you could find out the velocity or the acceleration of c. You could find it would also have an r omega going in this direction, and you could find just that x component. You can find the velocity of c. I don't think that's an easier way to do it. I think the absolute approach is more straightforward, and it's that's the method I wanted you to use. All right, this next one is the scalar problem, and we did this exact one in homework, so I was hoping that we'd have good scores on this one. The only thing I did was mix up A and D here. In homework, I think you solve for the velocity of B and the acceleration of D. In this one, I might need to find the velocity of D and the acceleration of B. And here we just need to know that V of C is equal to r omega, and the acceleration of c is equal to r alpha. Knowing those, you can find out the relationships there, or find out what those r omega and alpha are. And then let's just look at the velocity first. The velocity of d has two components. It has, if we remember our scalar equation, we say the velocity of d is equal to the velocity of c plus the velocity of d with respect to c, and the with respect to component is the r omega, as if c wasn't moving. So what would the velocity of d look like if c wasn't moving? Well, if c wasn't moving, this would be just rotating around in a circle like this, so that we'd have that r omega component right there. So let's just add those up. I know that velocity of A or C is going in at 1. Then velocity of D with respect to C is r omega. That's that r times this omega, which I've all solved for. And then I have a cosine, or I have an x component and a y component, which I solved for right there. The acceleration is similar. Before I go down to the equation, I just want to look at the picture here and just make sure you're okay with this. But the acceleration has an acceleration of c plus an acceleration in the normal direction and r omega squared in that direction, and a component in the tangential direction, which is an r alpha in that direction. And so each of these have I and j components, and you have to add them all up. So let's just go down and look at the equation then. Acceleration of b, which is that point right there, is equal to acceleration of c plus b with respect to c normal, b with respect to c tangential, and then the normal component is the r omega squared component, and it's got sine and cosine, and the r alpha is the tangential component, and it's got a sine and cosine, or I and j components, and yeah, just multiply them out and you get that as the answer. Okay, this one, there are two problems here. You had different versions, but this is the IC method, or the IC problem. And what we have to do is solve things in the IC method. We recognize the velocity vectors first. We draw perpendicular lines from the known velocity vectors to find the instantaneous center. Most people did okay on that. So let's just see what happens here. This is rotating in this direction, so I know that the velocity of A goes that way. V is constrained to move in this slot, so I know the velocity of B is going in that direction. Connect perpendicular lines from those velocity vectors. I find the IC is right there. I need to find that distance n and this distance m, and I did that with just sine and cosine. I need to recognize that VA here is equal to this r times that omega, and so I can find that that is equal to 3.6. But that VA is also equal to this total length times this omega. In other words, this triangle formed by the instantaneous center is all rotating at this instant about this point, so that the omega of this bar is the same as the big omega of this link times this omega. So I know the VA, and so I know m here, and I'm just going to say that omega of AB, this link right here, is going to be equal to 6. And then I find velocity of B is equal to this n times that same omega. It's going in this direction. All right, and I get that. All right, now the other picture is constructed slightly different, but it's equivalent in complexity. In this case, we have a rod pushing this, so I know there's a VC. I know it's going to be making this rod, or this link here, rotate in this direction. So I have to find the IC. I do that by connecting perpendicular lines to the known velocity vectors. In this case, I use the sine law to find out n and m. Locating VC is equal to this link here, this n, times this omega. This omega on this link is the same as that omega on that link, and I can find out omega BC. I can find VB by saying that it is now this link times this omega, and that's that. And then I can find out this omega here of AB by saying VB is equal to this length times this omega. And I think you can see all the math there. All right, this problem was slightly more subtle. I didn't expect everybody to get this, but here you have to recognize some some parallel velocity vectors. So let's start with this side over here, and we're going to say that this one rotates in that direction. We know VC has to go in that direction, rotates about that point. And I can find out VC by just saying that is this r omega. Now, what you'd have to realize here is this link here is rigid, that L-shaped rigid thing, and as this moves this way, it's going to push this way, but B can only rotate about A, which means that its circular motion about A, and that means its velocity vector has to be going in that direction. If I try to find out, then I see that these are parallel velocity vectors, if I try to connect the line, perpendicular lines to find the IC, I see that there is no IC, which means that there is no rotation of this bar. If there's no rotation of that bar, that means those velocity vectors have to be the same. And so I can say that velocity B is equal to velocity of C due to the parallel velocity vectors. Now I can solve for that one there. Now the car problem, again, this was a little bit on the subtle side, but what I was looking for here is to find the coefficient of friction. And because this is an inclined plane problem, we have just a little bit more work to do than we did with on flat. But in this case, the acceleration was given to us, and we're saying that this one has a rear wheel drive. So I draw a free body diagram, careful free body diagram. Put the force of friction back here. Oops, it looks like I forgot to label that force of friction, but it acts at the rear, pushing the car uphill. I got a normal force at each of those. I got an mg sine theta, mg cosine theta. So I can just say this force of friction, or excuse me, some of the forces in the x going up the hill is equal to mass times acceleration in the x. Mu c is what's pushing it up the hill. It's got an mg sine theta going down the hill, and that's equal to that. Now, if I to find out the coefficient of friction, I need to know that that normal force there. So I'm going to do a moment equation to find the normal force. So I'm going to sum moments about this point. I got this going in a positive direction. I got that going negative, and I got the sine theta going negative. And that's going to be equal to my mass times acceleration times its lever arm going in the positive direction. So find out C, and I can find out what the coefficient of friction has to be with rear wheel drive. Now, before I go on to the next part of the problem, we can kind of guess that if it's front wheel drive, what it might look like. Rear wheel drive, you can see where the location of the center of gravity is. It's probably got more weight on the front to go uphill, or in this situation, because the center of gravity is kind of on the front, which means that it probably has a higher normal force at the front, at B. If it has a higher normal force at B, in order to achieve the same acceleration of 2, I would guess that we probably don't need as much friction to accelerate up the hill with front wheel drive. But let's do the math here and just check this out. So with front wheel drive, we're going to draw the same free body diagram, except we're going to put the force of friction at the front. And we're going to do the same force in the x direction. Force of friction is mu b minus mg sine theta is equal to mass times acceleration going up the hill. And in this case, I'm going to rotate about c, or I'm going to sum moments about c going in the counterclockwise direction. So I have that mg cosine theta times this lever arm. Mg sine theta is now going in the opposite direction, so that would be negative. B is going in the opposite direction, so that's going to be negative times its lever arm. That's going to be equal to the mass times acceleration vector. And in this case, again, mass times acceleration is going positive with a positive counterclockwise lever arm around C. And I can solve that B is equal to 8272. Plugging that in there, I can see that the coefficient of friction required to get up the hill is 0.67, which is indeed less than what I found up there. And the normal force at B, we found it's 8272. And we say up here the normal force at C was 6219. So again, that gives us confidence, I guess, that with a higher normal force, we have a less coefficient of friction required to achieve that acceleration. And then the last problem was a tip and slip problem, and I had simplified this a little bit for you in that I gave you a lot of the information, and so tip and slip problems are generally pretty easy to solve because you can usually analyze the slip condition with one equation, and you can usually analyze the tip condition with one equation. Again, as an inclined plane, this makes it a little bit more difficult, but let's just look at the slip equation. So I'm going to say that, again, drawing a free body diagram, got an mg sine theta, mg cosine theta, got a normal force and a force of friction. If I'm talking about slipping, then the force of friction is equal to mu normal. Some of the forces in the y direction suggest that the normal force is going to be equal to that mg cosine theta. So the force of friction then is going to be equal to mu mg cosine theta, pushing up the hill. Got an mg sine theta going down the hill, and those are going to equal the mass times acceleration going up the hill. I can solve that for the acceleration. Given all those factors, I can say that The slip condition will happen if I try to go faster than 6.025 meters per second squared. The tip condition, assuming that it's going to tip, it'll tip around that back point right there. So let's just sum the moments about that point, the tip point. I got mg cosine theta times this lever arm, got mg sine theta times this lever arm, mg cosine theta times its lever arm, and that's going to be equal to the mass times acceleration vector. Now again, if this is positive in this direction, the mass times acceleration vector is going to be negative, so that's why I have a negative sign right there, and I can find that. In this case, the acceleration to tip and the acceleration to slip was exactly the same, so I'm just going to say that it slips and tips at the same instant. If the box is a little skinnier, that some of you had this question, it's a little bit different. The analysis is exactly the same, and we say that the slip condition can be analyzed with one equation, and the tip condition can be analyzed with the moment equation in exactly the same way. The answers are just slightly different here. Because it's skinnier, we can see that it will slip at 3.922, and it tips at 3.469, so that it definitely tips first. Anyway, I hope this makes sense to you, and we'll upload this and email me if you have any questions.